In some ways, that question is a circular statement. What's the probability that the p-value is less than 0.05 if the null hypothesis is true? Well, what is a p-value? It's the probability that you'd see data at least this extreme if the null hypothesis is true. Let me repeat that and see if I can get it to click that that's a circular statement. If the null hypothesis is true, the probability of seeing data like this, 0.05. What's the probability of getting a p-value less than 0.05? 0.05. Let me say it again. There is some particular cutoff. There's some particular type of data, some cutoff for our test statistic, such that we'd only expect to see data like that 5% of the time. And by definition, that's the cutoff for a p-value of 0.05. What's the probability that I see data like that if the null hypothesis is true? By definition, 0.05. What if I had chosen a different cutoff? What if I asked a different question? What if I said, what is the probability that when I do a simulation where the null hypothesis is true, the p-value will be less than 0.1? The answer is 0.1. Because there's some cutoff such that when the null hypothesis is true, I'd expect my data to be at least this extreme 10% of the time. That's the cutoff for the p-value of 0.1. What's the probability I see data like that? By definition, 0.1. What's the probability of seeing a p-value less than or equal to 0.1? By definition, 0.1. For any p-value cutoff I choose, the probability of seeing a p-value less than or equal to that value, by definition, is that value. The probability of seeing a p-value less than 0.05 when the null hypothesis is true, 0.05. The probability of seeing a p-value less than 0.1 when the null hypothesis is true, 0.1. The probability of seeing a p-value less than 0.37 when the null hypothesis is true, 37%. That's what we'd expect to see if we do a simulation, that 5% of the time the p-values are less than 0.05, 10% of the time the p-values are less than 0.1, 37% of the time the p-values are less than 0.37. So we could have stopped there, and in fact, many sources will. Many sources will. You'll often see in textbooks, the way we're going to check how well our test worked is to see what proportion of the time we reject the null hypothesis at the 0.05 level. In other words, we're going to assume the null hypothesis is true in our simulation and see what proportion of the time we get p-values less than 0.05. If that number is 5%, we know we're good. If that number is vastly less than or greater than 5%, there must be something wrong with the test. The assumptions must be influencing the answer we get. The assumptions must not be true in a way that's important. So we could stop there, again, and just say, pick some particular cutoff, like 0.05, what proportion of the time are our p-values less than that cutoff? However, in my view, since we have this understanding that whatever cutoff we choose, 0.05, 0.1, 0.37, that's the proportion of time we'd expect to see p-values less than or equal to that, we may as well just make a histogram of our p-values that has the property that 5% of the time it's less than 0.05, 10% of the time it's less than 0.1. What should that picture look like? What should that picture look like? I'm going to argue, I'm going to try to convince you, that that picture should look like what's called a uniform distribution. A uniform distribution is a distribution that's flat. In other words, a distribution that is equally likely to take on any of the values in between. P-values are continuous numbers. They can be continuous numbers between 0 and 1. But if we think of a discrete version of this just for a moment, if I roll a die, the distribution of the values I'd expect to see, 1, 2, 3, 4, 5, and 6, looks like a discrete version of the uniform distribution. In other words, each of these values are equally likely. Each of these values has a 1 out of 6 probability of occurring. And I want to convince you that this distribution here has the property that we've been talking about. What's the probability that if I roll a die, I get a number that's 1 or less? 1 out of 6. What's the probability if I roll a die that I get a number that's 2 or less? 2 out of 6. What's the probability I get a number that's 3 or less? 3 out of 6. The same thing is true if I draw the continuous version of this, where it's equally likely that I get a value between 0 and 0.2, between 0.2 and 0.4, between 0.4 and 0.6, 0.6 to 0.8, and 0.8 to 1. If it's equally likely that my values fall in each of these ranges, then the probability that I get a value less than 0.2, well, this is 20% of this picture. The probability I get a value less than 0.4, well, that's 40% of this picture. The probability I get a value less than 0.8, that's 80% of this picture. A uniform distribution is a distribution such that the probability that we get something less than any particular cutoff is equal to that cutoff if the values are required to be between 0 and 1. Note that I could draw this same picture, but with more lines in it, right? I could draw a histogram with more breaks, and now I can say, okay, not only is it true that the probability that I get a value less than 0.2 is equal to 0.2, I could also say the probability I get a value less than 0.1 is 0.1, and the probability I get a value less than 0.05 is equal to 0.05. The probability I get a value less than 0.37, let me shade that in there, 0.37. By definition of the way I drew this picture, which exactly parallels this idea. If each value is equally likely, or each range of values between two particular cutoffs is equally likely, then for any number I choose, the probability of seeing something less than that, or less than or equal to that, is equal to whatever that number is. Convince yourself that this is true. Convince yourself that this is true. The exercise I suggest is writing down some numbers that fit into this particular distribution. So for example, maybe you want to make a picture that has like the numbers 3 and 7, and then 13 and 18, and 23 and 29, etc. Right? For each set of 10 numbers, write down a couple numbers in that range, and then pick cutoffs and say, what's the probability that I get a value less than 20? And you'll see that it's approximately 20%. Convince yourself that this is true, and then we can use this idea for our simulations. Because if I repeatedly sample from population distributions, conduct a test, and get a p-value, if the null hypothesis is true, then if I repeat that process 10,000 times, I'd expect to see a histogram of p-values that's flat like this, such that if I choose any particular cutoff, such as 0.05, I'll tell you that about 5% of the time, those p-values were less than 0.05. If my assumptions aren't true, perhaps the picture will still look like this, in which case I can say this test was still valid. It was still true that 5% of the time I got p-values less than 0.05. This test was still valid when the assumptions weren't true. In other words, this test must be fairly robust to those assumptions. Sometimes that'll be the case. Or I might break the assumptions, and this picture will look totally different than this flat uniform distribution. Then I can say, this method does not appear to be robust to this particular assumption. This assumption must matter. Also, another simulation I can do is to change the truth. Maybe the null hypothesis isn't true anymore. If the null hypothesis is not true, then you'd expect to reject that null hypothesis as much as possible. Again, when the null hypothesis is true, then I hope I don't reject it more than, say, 5% of the time. Right? I have some type 1 error rate. I hope I don't reject it too often because it's true. But if the null hypothesis is not true, if something else is true, I hope I'm getting really small p-values most of the time. I hope that I'm rejecting that null hypothesis because that's the right answer. So if our null hypothesis is not true when I do the simulations that I'm discussing, then I'd expect to see a picture with a lot of really small p-values and then not so many big p-values. So I can assess what's called the power of my test, the probability that I correctly reject the null hypothesis when indeed it is false, by doing the same kind of simulation and knowing what I'd expect to see for those p-values if the null hypothesis is actually true, as opposed to if the null hypothesis is actually false.